not really, not really. Actually, when we use that's a good question. When we use ray tracing, the idea of ray tracing that we are following the path of rays which are cast from the center of projection. That's the idea. But what happens when we find an intersection? We find an intersection in a certain point of a mesh within a scene. So what? So what? We apply the Fung model right over here to calculate the color on that part of intersection. What ray tracing does is that gives you a tree of intersections for the same ray. For each one of the intersections, you compute the local color using the Fung model, which we still have to see, actually. And then you compose the values, the local color values that you got along the intersection tree, and get the final color. There is a composing algorithm which is added. But basically, the idea is that we apply locally the Fung model. How many times? Exactly as much times as we find intersection following the cast ray. Okay, thank you. Any other question? Because usually you are a little bit more than this. So, hello. So nice to see you. Please take your seat. Any other question? Shall we decide, shall we use this quality time to decide the dates of the exam? Oh, Paolo did it again. He always does this. He never checks his marker. That's okay. We should fix 2 dates, I guess, in February, right? For the exams. I usually pick 1 date in early February and 1 date in late February. So let's see if what we pick matches more or less any other date for your exams. For example, I could say Friday, the 6th of February in the afternoon. Would it be feasible as a first call? In February, Friday, the 6th at 15. No, 2009. 6th of February, 2009. It's Friday. Okay. I'm using technology here, mind you. And that's it. The second call should be somewhere late in February. So what about the 20th? 20th of February, 15. Does it collide with any other? It does. Which one? The 20th. Friday. That's an exam you have to attend. It's just a delivery. So you can deliver and then come to me. Okay, that's okay. So that's feasible. If I can suggest, this is typically the exam you would want to get rid of as soon as possible, because it's just a written exam with a lot of things to practice and memorize. So what you should do is start right away practicing and memorizing, practicing where you have the pencils, Then please pay attention that you have a set of pre-prepared exercises which are downloadable from the Course Online web page. There's a collection of exercises for for question number 2 in exam, where you are required to perform calculations. So like, for example, evaluate collision of a sphere against a plane, blah, 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 blah. There are 8 basic samples for 8 different kind of exercises you can get. So I warmly recommend to download those examples, follow all the calculations, try on your own, and be sure that you understand every step of those exercises, because what you will find on the exam will be a variation, well, small variation on those basic exercises. So it will not be the same. It will be with, I don't know, different numbers, or maybe a little trick, something different, enough to justify that you don't straight away copy from any kind of small paper that you might hide in your underwear or whatever. I had the most embarrassing anecdote once at an exam. There was a girl, and she was writing, and she had this kind of strip coming out from her underwear, from her trousers and from her underwear. You know that girls sometimes wear very short tops or whatever, so you could actually see, well, the top of her pants, and there was this strip coming out from her pants, and I was looking at that, and I don't know, is it computer graphics or not? So I was basically staring at her bottom, trying to understand if it was something related to computer graphics or not. So staring, and it was do not tumble dry and do not wash. So it was not computer graphics, definitely. But it's okay. Just to tell you a little story to tell you that I do check. So it might happen that what is this? Okay. So mind you, it's a closed book exam. Okay, any other question? So we fixed the date of the exam. I will write it for latecomers. So which dates we said? Exam calls. How was the seminar last time? I couldn't attend. But I told you that it was quite a little bit off the track. I mean, it was, interesting anyhow. I met the Fulvio woman a couple of days earlier and discussed with her about, her theories. Because in my research group, we do this. Actually, we use computer graphics for, completely different things from gaming. We use, in a broad sense, graphics to study interfaces, to simplify, human-computer interaction, basically. Right now, there is an ongoing project, you probably know by now, which is all geared on simplifying interfaces for people with cognitive impairments. And, we got in touch with this woman over here that she's making a study about different kind of cognitive impairments. So I think, anyhow, I always think that for us engineers, understanding not just technology, but understanding, what's around us, it's always an advantage, because our approach as engineers is to use technology to solve somebody else's problem. So we are always forced to understand what the problem is. It can be finance, it can be chemistry, it can be mechanics, it can be aeronautics, it can be psychology. Down to the earth, we use our engineering to solve problems in other domains. So that's why we are usually required to understand different domains than specifically ours. So multidisciplinary approach is always a winning frame of mind. Mind you, if you want to cooperate in such projects, I'm always open for that. So if you want to do something different as your thesis, you can just ask to have a meeting, and I will show you what we are doing. And if you're interested, there's always a lot of work to do. So you're welcome for that. While I was chatting, for those of you latecomers, we decided the exam calls, and we are going to have the first call for computer graphics on February the 6th. 6th of February 2009 at 15 hours. Okay? 15 hours means 15 hours. So be there at 15, not 15:15 or 15:30. That's 15. Okay? And the other one, if I'm correct, should be the 20th, right? Okay, February 2009, same thing at 15 hours. Come in. Somebody knocked? Oh yes, my friend. Grazie. So, sì, perfect. So, evaluation time. So, place your hand on your heart when evaluating. And, okay, that's it. Prego. Eccole. Sì, ma perché volevo mettermi d'accordo con loro prima. Adesso gliele scrivo, anzi gliele scrivo subito mentre che lei è lì. Com'è Giuseppe.evolvi? Ok. Вот это правильно. Ты совсем не английский, ты русский. Non ce li abbiamo in russo? Non ce li abbiamo in russo? No. Hello.
Evaluation in Italy or Italian?
English or Italian?
English?
È vero, di solito ne ho di più.
Ma come è stata poi con gli ospiti?
Non so, mi sembra che hanno girato un po' per le aule e alla fine si sono messi d'accordo dove incontrare.
O come mandavo
Sì, sì, sì. Boh, non so.
Dopo non ancora dove l'ubiquità.
Don't copy. This course, it's about me. This is the new university. Students give grades to teachers, and not the opposite. Allora, il 9 gennaio avevate un'esercitazione che è stata spostata, anticipata, l'ultima l'avete fatta settimana scorsa. E io ho la mia lezione il 16 gennaio. Perché? No, non possiamo perché è incastrata in un'altra cosa. Ecco, a colpa... Sono il primo?
Il primo di qui c'era uno primo di là.
Sì, giusto appunto adesso. Surfaces. Così difficile da compilare, sembra difficile da compilare. Non so. Grazie a lei, arrivederci. Okay, last time, if you remember, we finished by playing around, fiddling around with Nate Robbins' tutorial about light and materials. We've been fiddling around a little bit, and we discovered that in Fung's model, and in OpenGL as well, which completely supports this lighting model, you have basically two groups of settings, two groups of matrices. One is related to the light source, the other one is related to the material. The peculiar thing is that even at light source level, you are required to subdivide the parameters describing your light source, not only according to the three primary channels which are usually used in an emissive system to describe colors, namely R, G, and B. They stand for red, green, and blue. But you have a second level of subdivision which is related to the interaction characteristic of materials with light. The three basic ways in which materials can interact with light emission is ambience, then diffuse surfaces, and then specular surfaces. That is, for every light source, you can specify what is the intensity of emission on a given color channel for a given material interaction type. Therefore, you specify 9 parameters, which is the behavior of the red channel for the ambient contribution of light, the behavior for the same red channel for the diffuse contribution, the behavior for the same red channel for the specular contribution. Same thing for green, same thing for blue. In total, you have a matrix of 9 parameters for each one of the light sources which are present in your scene. Usually you don't have a single light source in a scene, but you have many of them. Like, for example, consider this very scene in which you're seated right now. There is 1, 2, 3, 4, 5, 6 if you count the projector light sources, then probably some monitors over here if you want to go fine. So you have a lot of light sources. For every one of this light source, you have to decide which kind of light source it is, namely a point source or a spot source or a distance source. So there are different kinds of light sources. And for each light source, you have to describe its 9 emission parameters in terms of each one of the color channel and the contribution for ambient, diffuse, and specular surfaces. Then you have to combine this emission matrix with the other matrix, which is describing how specific materials are absorbing or reflecting color. And that was the lower part of Nate Robbins' tutorial, if you remind that, where I could specify absorption parameters. Namely, I compute a parameter to 0 to describe the fact that I didn't have reflection, but I had total absorption. And I have one of such, how can you tell, levers, parameters, for each one of these combinations. So I can specify, for example, for specular red, this specific material is completely absorbing any specular red. That would mean that the coefficient K for red specular would be 0, which means that you will not have a specular appearance, at least not for the red, for that specific object. These were the experiments that we did last time with the tutorial. If you don't remember or you're not quite clear with those, you're encouraged to Google for Nate Robbins and download the tutorials. I think they're available from my page anyhow. But if not, you can Google them. Nate Robbins is N-A-T-E space R-O-B-I-N-S, Robbins. Google them, download them, use the tutorial for light and matter, fiddle around the parameters, and you will soon understand my meaning. Okay, but we did that together last time, so you should remember. Okay, let's go a little bit further. In describing, I briefly already mentioned them, but let's describe a little bit finer which light source you have considered in the model, in fun model, and how you can represent them in vector form. In order, because my ultimate goal is to describe the Helmholtz equation as a matrix equation that I can solve to get numbers. Numbers that will represent the intensity of color on a certain point in surface, intensity which I will, in a second step, convert into the RGB quantized color step. You remember we did this earlier in this set of slides. I warned you that the result that we have is all intensities. But light intensity is not what my frame buffer needs. My frame buffer needs a value, usually from 0 to 255, but that really depends from the bit depth of your frame buffer, the color depth of your frame buffer. And you have to convert the intensity that you get here from this kind of calculation into a level, a color level, into a number from 0 to 255 for each one of the channels. How do you do that? We've seen that it depends from a logarithmic scale, which starts from the minimum viewable intensity of your specific viewing device. Knowing this parameter and knowing depth of your viewing system, then you can derive backwards the quantization step, the quantization level for each color channel. We did that with the formula in the beginning. So that's for intensities. So mind you that we are talking about intensities and not color levels, that you have to convert to color level afterwards. For ambient illumination, what's ambient illumination? It's a special kind of illumination whose definition is the intensity given by ambient light source is such that you have this intensity equally distributed in every part, in every point of your scene, independently from the real distance of this light source. So, for example, light coming from the window, ultimately coming from the sun, actually, could be considered ambient light because it goes to have an effect which is the same effect on any triangle of the mesh of this scene in the same way. So it has a contribution which is constant in every point of the model of the space you are considering. Therefore, it is simply stated like this, like a vector for the three color channels. What is the ambient intensity for red, the ambient intensity for green, and the ambient intensity for blue? This factor will be summed to all the other factors as it is, because it is considered independent from the specific position of the polygon you are considering in space and from the distance of the light source. Because the light source is so uniform, it's so big, it's so distant, that it actually doesn't make any difference that you are considering what is the impact of this specific light source to this point or to this point. It doesn't make any difference because you're considering the impact of the sun, which is already millions of kilometers away. So we just consider it as constant. That's ambient, that's easy. Basically, when you have an ambient light, how do you, in general, what is in general the idea of getting the whole intensity in one point? Well, this is for the red channel, the example. This is a formula that gives you how can you calculate the intensity given by a specific light source, the light source I, for one channel, the channel red. It is given by, there is a part which is given by the ambient part of the light source and the absorption matrix of the material for red. Then the same thing but for the diffuse, red but diffuse. Then the same thing, red but specular. to all of this, if you have defined an additional light source, which is classified generally as an ambient light source, you have to add as a whole the contribution for the same color channel of that ambient light source. So, for example, you have 1, 2, 3, 4 light sources. These are not ambient light sources because they are near, well, they are very near, they are specific in a point, and they make a difference. I mean, if I'm directly under it, I am lit in a very different way if I were, I don't know, sitting in the corner right there, right? So they are not ambient. They have a variable influence on objects on the scene. I have 4 known ambient lights, and I have 1 ambient light, which is the window. How do I compute the general intensity of a specific point? Let's say this one, this point over here. I will sum. Each one of these is described by a matrix, right? The matrix L. But the matrix L itself has an ambient column inside. Do you remember? Over here. Every light source is described with a diffuse part, a specular part, and an ambient part. Okay? If you want to say, hey, this light source is very near, it doesn't have any ambient-like behavior, then it's up to you. You define this light source with 0, 0, 0 as an ambient factor. But if you want to say it's local, and it has, for some reason, that, well, it depends on you that you are the light designer and the scene designer. If for some reason you want that light to have an ambient level impact, then you can model it with this column over here. So, in short, for each one of the lights you are considering, you are computing the emission matrix with the absorption matrix for the ambient part, the diffuse part, the specular part, for every one of the lights which are shining on this point. So from that, from this one, from that one, from that one, from that one, plus the ambient light, which is the window over here, right? So this is how it works. Look, this is still, actually is not saying anything much. It's just saying a global process. Now there is the problem that you have to determine this, this, and this, and you have to do it in different ways according to specific situations. The only thing that is very neat, is very straightforward, is if you have ambient light, you add it everywhere, anyhow, like this. The only thing you have to pay attention is that you add the color, the right color channel contribution to the color channel that you are computing in that moment. And you have 3 of them, R, G, and B. Okay, that's for ambient light sources. But then, when you consider locally working light sources, then the first question you have to ask yourself is, which kind of light source is this? This is one of the possible kind, which is a point source. A point source is most convenient because it's defined as a source which emits light in a uniform way in all directions, and per se, it has no extension. It's a point. So it's a point with no sides, emitting in a uniform way in all directions. This is very convenient because if it had a surface, then we should perform an integral over all the points in volume of its surface, which we don't want to do. Okay? So we go short, and we try as much as we can to collapse all light sources, which should more or less behave like this, not like I am going to describe to you right now, to a point source. So we don't give a fact that it actually has an extension. We just say, okay, it's a point source, so I don't need any integral. Okay, it's a simplification. The only thing I have to I beg the ladies to pardon my French. Do you know this way of saying, pardon my French? Okay, the English, when they swear, when they say bad words, they always say, pardon my French. Because they say that French anyhow is bad words. So when they're saying bad words, it's like they're speaking French. So it's pardon my French. And what I was saying, yes, the only thing that you have to pay attention to is the distance. The distance here is the variable you have to take into account. The variable that you did not have when you were considering ambient lights, because ambient lights were considered to have a uniform effect regardless of the specific point inside the scene. So it was independent from distance. But a point source depends from the distance. This is your source. This is the point you're considering in the mesh. The intensity which arrives on point P because of an emission from point source P0 can be described as the intensity which is emitted from P0 divided by the square of the distance, where P0 is the intensity here in red, in green, and in blue, okay, which has to be obtained like this, right? That is, you have to know the R of the material directly in the light source and the L of the light source. This, I know, it doesn't make any sense physically, but this is the way it works. You have to know, the process is this. I'm calculating what is the effect of source P0 shining over P. I know which material P is made of, so I'm starting to calculate IR, IG, and IB, and for calculating this, I not only need L, which is the characteristics of the light, which is strange already enough, because already the characteristic is described as ambient, specular, and diffuse. But also, I have to take into account R, which is specific of the material of which the mesh is made of. Once you have this, you still have not finished. You need to calculate the distance. Square it and divide it. This is the distance, this is the intensity you perceive at the point. It's a vector because it actually summarizes red channel, green channel, and blue channel, right? This is still not your RGB color, of course. First, because you should stop and consider if there are any other sources which are going to impact on P, and if so, you should go on adding. Secondly, because you have an intensity and you have to convert it to a quantized step. So those are not RGB level, but intensity levels. There is a trick. The problem in defining the light sources in this way, I think I have a picture, right, is this. That point sources in nature do not exist. Light sources in general do have an extension, a surface. Therefore, if you approximate everything to a point source, you lose umbras and penumbras. What are umbras and penumbras? Consider a light source with an extension and consider an object which is lit by this light source. What you have is that you have a different way of projecting shades because of the fact that every little point in the light source is actually a point source. So you have points in which you have full light, points in which you have half light, and points in which you don't have light any at all. This kind of effect you don't have with a point source. Therefore, if you light your scene only with one light source, the result that you have is extremely harsh. It's everything either very light or very dark. You don't have anything in between. There's not much we can do except adding more ambient light. Well, if you ever tried drawing something in a 3D drawing environment like Blender or 3D Max or whatever. And if you never tried, you can try if you want in the second semester with the course of computer graphics application. One problem that you have, you immediately realize this as soon as you do your first render, is placing the lights in good places. You place one light, you render, and everything is mostly dark, and when there is not dark, it's very shiny. So what do? You start placing lights all around until you have a good lighting condition. But this, everything stems from the beginning of the fact that we collapse in calculation. We tend to collapse lights to a point, and we tend to lose this kind of refinement in modeling lights. There is a different kind of light that helps a little bit, and I will show it to you later. But with point sources, you have that problem. One small trick that you can use to reduce harshness is, instead of using a plain square for the distance, you use an attenuation polynomial, which is this. You attenuate your emissions by using a quadratic polynomial where usually, well, d is the distance, and a, b, and c are attenuation factors. These attenuation factors are something that you decide as a light designer or as a model designer. You try with some numbers, and if you don't like the result, you try with different numbers until you find numbers that give you satisfying aesthetic results. For the sake of the exam, when you want to apply in your calculation the attenuation polynomial, I will give you the values for A, B, and C. Okay? So you will just, this is just because in that way we all get the same numbers, and I don't get crazy performing 50 times 50 different calculations because everybody chose a set of 50 different sets of attenuation constants. Okay, but we will see an example. Okay, that was the point source. Now, for another kind of light source, which is the spotlight. The spotlight has a position which is a specific point, but it also has a direction, which is not the case with the point light, which emits in a uniform way in every direction. Not so the spotlight, which emits only in a narrow volume, which is modeled with a cone, oriented to a specific direction. So to define a spotlight, I use the point in which the spotlight exists. Salve, dica. Cosa ho combinato adesso?
Computer graphics nel primo semestre di quest'anno.
Ah,
Due dati.
sì,
Sono l'ultimo per l'anno.
ce ne vuole una sola. Faccia il 20. Grazie, scusi. Then you need to know a vector which describes the direction of the spotlight. And another thing that you can use is a distribution factor which describes how light intensity is distributed within the cone. You could, for example, specify that most of the light is toward the center of the cone, like here, for example, or that there is a more smoother distribution of the intensity within the cone, like this, for example, and so on. You model this like a cosine, and usually this also is a parameter which is given. So we will call it beta. Beta will be the distribution of the light intensity within the cone. Then we will use U as a direction of the cone, a direction vector which is called U. And small l is the direction between Q, the position of the light source, and P, which is the point in which you are considering the illumination. This is different from U. You can understand that because U is the direction in which the spotlight points. And L is the direction between the position of the spotlight and the point in which you're considering illumination. They are not necessarily the same. Right? Like, for example, I'm illuminating with a spotlight over there, in that direction, but I want to consider the effect of illumination on that point over there. So U will be like this, and L will be like this. And the position of the spotlight is here. Right? So you have to consider that, and the distribution, and an attenuation polynomial. So the distance. Now there, we have everything we need to describe the Phong model. So the Phong model is a recipe, well, a method, to calculate colors, as I told you, in a very empirical but effective way. This was a method devised by a researcher, Phong Bui Tuong. I think he's Korean. And after that, well, Phong's approach was immediately extremely widely adopted because of its simplicity and its effectiveness. And until now, OpenGL and all other renderers, when they want to render in real time, and even not in real time, for example, in ray tracing, as we were discussing at the beginning of this lecture, until now, the Phong model is still used to make this kind of calculations. Phong model requires you to calculate 4 basic vectors, which you will use for all the following calculations. This vector, you consider a mesh and a point on this mesh on which you want to calculate the color. Then you have to determine these 4 vectors. N is the normal in the point you have selected to the surface you are considering. You can think, to simplify things, as a surface like just one polygon. Okay, so one polygon, one triangle, the normal to that polygon belonging to the mesh you are considering. Then you need V. It's the direction from the point you are considering to the center of projection. It will be COP minus P in a way that all vectors are outgoing from the mesh. COP is the center of projection where all visualization takes place. Then there is L. L is direction from P to the light source, the position of the light source. So it will be S minus P. Then there is R, which is the direction of perfect reflection in P from L, in this direction over here. There are a few methods to calculate it, and we'll see it. We'll see them. Okay, so N, V, L, and R. N, the normal, which gives you the orientation of the surface. L gives you the mutual position between the viewer and the surface, the observer and the surface. I'm sorry, V gives you the mutual position between the observer and the surface. V stands for viewer. L, the mutual position between the light source and the surface. L stands for light. And R is the direction of perfect reflection. R stands for reflection. Okay, this I already told you. It's about using the KAB, KIR as a reflection coefficient. You do it in ambient. This is explaining how that air matrix actually works. For an ambient reflection, it works in a straightforward manner. That is, you have a coefficient for ambient for each channel. You just apply it to the incoming intensity. So you will have a K to apply for ambient light for blue, for red and for green. If this value equals to 0, then you will have maximum absorption and no reflection. If this value equals to 1, then you will have no absorption and maximum reflection. It's how it works in Nate Robbins' tutorial, as we have already seen. Then Fung says, okay, that's one. The other one is, how do I represent with simple mathematics reflection for the diffuse part? First of all, we have to understand how reflection behaves in diffuse surfaces. Why a surface has a diffuse appearance? Because it's rough on its surface. Rough means not smooth, not completely polished. Because of this, because the surface is rough, if you could see it with a microscope, you could see that its surface is actually not smooth, but a continuous series of mountains and valleys, very ragged. For this reason, when a ray of light is incoming to a surface, it could come and reflect in very different direction, because it depends from the actual point in which light falls. You see, it reflects in different ways. For this reason, the effect is that light does not reflect to a preferential direction, but gets scattered all around. This gives you a diffuse look. This is the reason of why diffusion happens. Another concept that we use is called Lambert's law. Well, Lambert's law could be stated like this, that on rough surfaces, because of this way of rough surfaces work, we always, this is how actually what the law says. The law says in rough surfaces, it is possible to perceive only the vertical component of the intensity. What is the vertical component of the intensity? It's easier to understand it like this. Imagine your girlfriend laying on a sunny beach at midday. Then the sun is exactly upon her. She is fully in light. She completely gets all the light from the sun. She gets burned. Right? Then consider again another girlfriend, which lays on the beach, but at 6 in the evening, when the sun is not exactly on the top, but is actually inclined. What she is getting is not all the energy of the, well, the sun hasn't changed energy. The sun is emitting the same quantity of energy, right? But the position of the girlfriend in relation to the sun matters, because the girlfriend takes only the vertical component of the energy. That's Lambert's law. He actually discovered this law by looking at other people's girlfriends on the beach. So when the light source is completely vertical over the surface, then the vertical intensity coincides with the emitted intensity. You get the maximum value of the intensity. But why? Because it's vertical. You get the vertical component, you get the maximum intensity. But if your light source is not exactly on the vertical, then the real intensity that you get from the light source depends only from actually the cosine, from the vertical part. So, having adopted Lambert's law, Fong says we need to know the mutual position of the light source and the point I am considering. Why? Because for the diffuse part, this happens. But you could say, but where is all the other energy going? Because actually the energy involved does not change. It's like, Lambert says, that it's like actually you spread the illumination energy over a wider surface. So that any delta of surface is actually getting less energy than before. Why? Because the energy is spreading on a wider area, as you can see in the picture. That makes sense. There's balance. So this is what we're going to consider in the formula I am proposing now. So basically you need to know the direction of the light and the orientation of the surface you are considering. Why? Because basically, I told you the vertical component is the cosine of this angle, but the cosine of this angle is actually a scalar product between L and N. Okay, N is this one, and L is this one. Right? So you get this cosine by definition using the scalar product between these two. So your intensity for the diffuse part is given by the emission matrix of your specific light source. Then you have the R part, which is actually a coefficient, 0 or 1, as we have said. But you have to take into account that this depends from the position of the light source and the mutual orientation of the surface. So you have to multiply everything by the cosine. Plus, if you are using a point light source, you have to take into account that you have an attenuation which is basically dependent from the distance. Then you have to take the distance into account too. So I have added over here the quadratic polynomial for distance. Mind you that if your light source is not a point light but is a spotlight, this is not the equation to go for, because then you have also to consider what? Do you remember? You have to consider this. The direction in which the spotlight is shining. L again, and beta as a diffusion. So it will have an additional part over here to take into account for the direction and the internal distribution of the spotlight. Okay, it looks complicated, but actually it's not. And it's much less complicated than doing a 5-time integral in 5 variables. Do you remember? I've shown it to you at the beginning. That's the theoretical general illumination equation. Okay? It's 5 integrals along x, y, z, theta. I think it's 6, not 5, because x, y, z, theta, phi, because you need the polar coordinates. And then you have lambda, because you have to do on all the emitted wavelengths of a specific source. Okay, that's it for diffuse. So when I have sources with a diffuse part, the diffuse part of the emission has to be treated like that, using Lambert's law. Then we will see an exercise at the end, so everything will be extremely clear, I hope. Now, ambient light we have said, diffuse part we have said, specular, the specular part. How does specular reflection behave? For this, Fong, remember when he was a little kid, and he was laying in bed Sunday morning, wanting to sleep. But at that specific time, it's a sunny day, sunny morning day. He's laying in bed. Somebody from the house just in front is opening a window, and there is a specific moment, at a specific angle, in which that window reflects the sun. And you, in your bed, get a very shiny light of ray directly in your face. Did it ever happen to you? It's just for one fleeting moment, for 1 second, but there is a lot of energy from the sun, all concentrated in your face. Why? Because there is exactly the very same precise angle of that window, getting the light from the sun, reflecting it exactly on your face. So what does this story tell you? That for specular reflection, mirrors, or glass, mirrored glass, what it counts is the position of the viewer, so Mr. Fong laying in bed, and the direction of the reflection of the light source. Because it's the sun shining on the old woman living in front window and going directly into your eyes. So everything reduces to knowing the reflection direction and the viewer direction. The cosine of these two actually go to 1 when the viewer is exactly aligned to the direction of the reflection. You see? That's what R scalar V means. Means that you have 1 when you are perfectly aligned, and 0 when you are perfectly orthogonal, in which case you don't see anything from that specular reflection. And this is exactly what the scalar product tells you. Do you see its meaning? It has a very nice, very clear geometrical meaning. Just to complicate things a little bit further, you have an alpha coefficient, which is called shininess, which enhances a little bit at the exponent the perceived intensity, giving you an effect of better or more sparse concentration of light. You remember we fiddled around with it a little bit during the end of the lecture last week. It has the effect to concentrate the shine on your object. So with very high shininess, you have a mirror-like, metal-like appearance, that is with a very concentrated shine. And below 100, the highlight is a little bit more diffuse. So if you want to get a rather noticeable metal-looking effect or mirror-looking effect, you can also play on a shininess factor, bringing it with a value around 100 or 500. More than that, you destroy everything. But with a value between that range, you can fiddle around a little bit and find right shade of your specific effect. So that's the whole baby altogether, which considers the diffuse part, the specular part, and the ambient part, with the coefficients, and with Lambert's law and the specular law, reflection law in place, with the attenuation factor. This is valid for a point light source. For spotlights, you still have to take into consideration the minus u scalar L to the power of beta factor. Okay. I think it's time to see it in action. Yes, almost. The only thing I have to tell you is how to How to calculate n, you know. Right? It's a vector product. How to calculate L and V, you know, if you know the position of P and the position of V or of L. It's just the difference between the two vectors, the two coordinates, two vector coordinates. What you might not know is how to calculate R given L. So how to calculate the perfect reflection. So okay, normals, for your benefit, if there is a review over here on how to calculate them. Oh well, what the hell, we can see it briefly. Well, the easiest way is this one. See, the vector product, as I told you. If you know, for example, you have a polygon, so you have the three coordinates of the polygon, P0, P1, and P2. What you can do is start from the coordinates of the vertices to get two vector directions. For example, by doing P2 minus P0 and P1 minus P0. This way, you convert these three vectors, which are coordinate vectors, the fourth coordinate is 1, to two vectors which are direction vectors with the fourth coordinate to 0. With those two, you make a vector product. This vector product gives you the normal to that polygon. That's an easy way, quick and dirty. How do you know which is P0, P1, and P2? It depends from the plotting order. Where do you take the plotting order? All the points are usually loaded in an array. You can use the position in the array. That's the plotting order. There is a much more difficult way to calculate normals. That is making a scalar product from a parametric surface. It involves creating a partial derivative over the parameters and create a scalar product, a vector product between the partial derivatives on the two parameters. What you get is, in effect, the normal. But this is not the way we have to go, because we would be forced to implement an algorithm to calculate analytically partial derivatives, which we don't want to do. Yeah? Sorry? Yeah, that's sine. Sorry, this is sine. Cosine and sine. Yeah. This is an example with a sphere. This is the parametric equation of a sphere. And just a very, very quick demonstration that it works with a sphere. But okay, it's just another way. But the way we will use is this one. Okay? I will give you three coordinates. With these three coordinates, make a triangle. In those order, subtract the coordinates to create two vectors. I'm sorry, right hand. Then create the scalar product, and you get the normal. And you have the normal. For L and V, you of course need the position of the viewer, the point you are considering, and the position of the light source. For R, this is the last thing that you need. You need to know L and N. Given that, you can obtain this by subtracting twice the perpendicular component of L over N. Okay? So you have L, you subtract, this is the perpendicular component, you subtract it one time, you get this, you subtract it another time, you get this, which is R. Therefore, you can find the reflection vector like this, L minus 2, perpendicular component of L over N. Let's solve a little bit better. Is 2 scalar between N and L multiplied by N minus L. Okay. It's something that you can think for yourself once you know how to obtain it, or you can memorize. For the sake of completeness, this is the refraction vector. We will not be handling refractions in our exercises, but for some renderers, especially if they are global renderers in which you want to model, for example, also glass, or in any time you need transparent materials, if you want them to do it reliably in a fashion that they look real, then you also have to take into account that light refracts over certain materials. And in that case, you need to calculate the refraction of the ray that you are following. And for that, you actually need the direction of entering of the light from material A into material B, material L into material T, whatever it may mean. And you need to know coefficients, density coefficients for each of the two materials, because you are going to plug everything into Snell's equation. Do you remember the equation of Snell? Snell's equation is actually the equation for refraction, applied in a vector form over here. So, well, it's just for the sake of completeness. If by chance you need to model refraction, then you can go to these slides and you can find them in a vector form ready for you to use. Okay, I would say I would take 10 minutes break if you're, because I see people sleeping here. So go and take coffee, strong one, because next thing that we're going to do is, you see we have a pencil here. Try with a practical example to apply this theory, putting some numbers in and see what are the steps we would have to follow to calculate colors. So, see you in 600 seconds. Sì.
Lei prima parlava di spotlight, diceva
drawing actually move around with the video. Or maybe you want to grab inside a video and move something around to where it wasn't before. Or maybe you just want to add thought balloons to videos of your friends. Take a look at some of the technologies I've been developing to do just those things. For example, here's my interface for drawing graffiti on objects in a video. Just click 4 corners of a rectangle you want the graffiti on, enter in the text, and that's it. Now you can scrub forward and backward through the video, and the graffiti is instantly attached to all the frames. Now, it's also possible to do this kind of thing with advanced motion graphics software, like Adobe's After Effects. But there are a lot of steps, and it takes some know-how. Even expert users take at least 5
Welcome back, survivors, to the last stint of our lecture. So, in theory it looks nice, but what if I had to apply this in practice? And more specifically, what if I have to do it during the exam? So this is what you have here, is taken from a question of an exam. So it's an exercise with a solution, but it's particularly helpful. I'm going to put it here so it will stay fixed. It's particularly helpful because it guides you step by step in performing all the calculations you need to extract illumination levels from a very simple situation. Of course, in real computer graphics, the situation is much more complicated than this, because here you have, well, if I'm not mistaken, one light source over here with its illumination matrix, and one triangle over here. So it's a very simple scene with one triangle and one light source, which is rarely the case in modern applications. But you start with 1 penny and you go on until you get 1 million, right? So let's start getting the penny. Consider a point light source S having the emission characteristics described in the matrix L. There you have. For your comfort, I also put a symbolic version of L, so you know what is LRA, what is LBS, and so forth. So I remind you that, for example, LRA means the illumination emitted for the red channel for the ambient type. LBS is the illumination for the specular type for the blue channel. Calculate the resulting light intensity I in the vertex P of a triangle of a lit mesh. A lit mesh means that there is a light shining on the mesh, defined by the vertices PQR plotted in the given order. Why do I care about specifying this? Because you want to apply a vector product to find the normal, and to apply the vector product you need to create two vectors coinciding with the sides of this triangle. And to get the direction of the normal right, you need the right direction of the two sides. So you need to follow the order. The viewer is located in COP. That's the position of viewer. Calculate the four main vectors of the Fung model. It doesn't say here which are the four main vectors, but you know that they are N, L, R. I don't remember the fourth one. Very good. Actually, I did remember, but knowing that the material of which the mesh to which the triangle belongs is such that its diffusive, reflection, and ambient coefficients are all equal to 0.5, that's the R matrix, and that its appearance is not metallic, that's for the shininess. So it says choose a shininess which is below 100. Calculate the resulting intensity on the vertex. Determine the necessary RGB levels to express the color in a 24-bit frame buffer. Why do you need this? Because you need the color depth in order to know the number of quantization steps in which you are expressing the intensity. Maybe it's just the case to remind you that in a 24-bit depth for a color buffer, it means, since you have 3 channels, that you have 256 steps for each channel, because it's 8 bits for red, 8 bits for green, and 8 bits for blue. Right? So do not make the mistakes to say that you have 2 to the 24 steps for each channel, because it is not so. Okay. Okay, let's start with the 4 main fun vectors. First one is the normal. The normal is obtained with the little trick that I taught you earlier before. That's why you need to know the order of the plotting order of the vertices. Once you do this, you find this normal. The normal is it of unit length. To check it, I calculate the norm, and I find out that its length is 1.414. This means it's not of unit length. This is not good for my health, because when I work with pure directions, it is best to work with pure direction expressed by vectors which are of unit length. Why is that? Because when I'm performing multiplications, I do not want the length of the vector to interfere with the result. Can you see that? And this is exactly the case when we are performing func calculations. In func calculations, we actually do not care about, well, consider, for example, the L vector or the V vector. We do not care the actual size of this vector. We care about the direction. If we carried on with L and V with a length which is higher than 1, since we are putting them in a series of multiplications, this would have an impact on the value of the intensity. Do you see? The intensity would change according to the size of L and V, and this is not correct. This is not Fung wants. Fung tells us to stick to the direction. And since we do not want the size of the vector, the length of the vector, to interfere with the result of the intensity, we need absolutely in all the 4 vectors to normalize them to unit length. In this way, even if I multiply them, their length, since it's 1, does not change the final result. Is it clear? So it's not unit length. We have to normalize it. How do we do that? We divide each component for the scalar, which is the length, and this is the result. Look, it's best for you actually you easily recognize that this number is the square of 2, right? You know that. It's best during the exam, if you are able to stick with symbolic calculations. That is, obtain this as 1 squared plus 1 squared over square root, under square root. Result, the square root of 2. Keep this result as the square root of 2. Do not translate it to 1.414. Why? Because if you are translating it to 1.414, you are already losing precision. When you arrive to the end, your result like this gets completely different from the actual one. Here actually I was the lazy one, because as you can see I'm using something which is called MATLAB. And it's very handyful, because you just type things and it's like a Word page, and I just change a number inside and add a few things, and all the calculations are done, so I can prepare the exam in 5 minutes. This is also why you have 8 basic standard kind of exercises, because there are 8 MATLAB templates that I'm using. But it's okay. I mean, if you don't know how to do it, you don't know how to do it. So, it really, in the end, it forces you to get the examples and study the examples, which is exactly what I want. So, in the end, I obtain what I want. But this also means that I cannot carry, in a consistent fashion, symbolic calculus. But you see, I'm trying it over here. There is a function in MATLAB which is called factor, which translates in symbolic representation numbers. So you can really see that this one, which is 0.707, is actually square of 2 over 2. Right? 0 and square of 2 over 2. That's the result I would expect, square root of 2 over 2. Which brings me to yet another discussion. Actually, this one should be 2 over the square of 2, right? 2 over the square root of 2, I'm sorry. Because it's, I'm sorry, 1 over the square root of 2. But it's a good practice never to leave fractions as non-rational. And in this case, if you put the square root of 2 in the lower part, in the denominator, then you have a non-rational fraction. But what you could do, what you should do is rationalize it. How do you rationalize it? It's very simple. You multiply for the square root of 2 above and below, and this is what you get, which is square root of 2 over 2. Okay? This is the ideal result. Okay, same thing over here. Then we need the second fun vector, which is v. That's by definition COP minus p. COP I do have, p I do have. So it's just a matter of subtracting the two babies. And of course, it's not of unit length. So I calculate the norm, and this is the viewer's unit vector, which is minus square root 2 over 2 minus square root of 2 over 2, 0. Usually, I design my exercises in a way that is perfectly possible to do it almost everything, not even with calculator, but by, well, manually. So if you start getting things like, I don't know, 1,372 over the square root of 9699.22, there is something wrong, because usually the numbers are very even. I do it on purpose. My goal here is not having you making a lot of calculation, is having you following the right procedure, right? Then there is L. This is the light vector. I had a small naming problem over here because I couldn't use L in my template because L was already taken for the illumination matrix. So that is why I labeled it H. It's like and okay, this is S minus P, 2 to 0, same thing, normalize. This is the light source unit vector. Then you have W. W is R. Same thing, I renamed it because I used the R for another thing, which is the third point of the triangle. So I'm sorry it's a little bit confused over here in respect to the slides, but I mean you can follow it anyhow. Notice that everything here I'm using over here is the normalized vector. So this is my unit vector for the ideal reflection. Also gets normalized. Now I'm happy because I have the 4 vectors. This is the first. I answered already to the first question, well, the first sub-question of this question. So question 2.1. So I got 2 points. Okay, I told you already, Thom's vectors have to be normalized prior to use and rationalized. By rationalize, I intend exactly that thing of multiplying on top and above and bottom for the square. Then we look at the emission matrix for the source, shows that there are no ambient contributions to add. So the text of the exercise doesn't mention any ambient in general, and if I look at the ambient contributions over here, they are all to 0. Actually, I realize that this light, of what color it is a pure green light, because it only has green diffuse and green specular, so it's only green, which of course I did on purpose, because otherwise we had to do everything again for the red, whatever. So it's only green, and only for diffuse and specular. but you have to take into account that you have to calculate the diffuse contribution and the specular contribution, because your light source has a specular part and a diffuse part. We will do it very soon. The first thing I need, since the source is a point light source, is to calculate the distance between the point I'm considering and the source. So here it is, and this is the distance. Then I consider an attenuation factor over here. These are the factors A, B, C. This is the attenuation polynomial. Unluckily, there is a difference in the polynomial as it is used here and as it is used in the slides. So if I recall, okay, this should be B. AD plus BD plus C. So that's the mistake, basically. So this is a B. And it turns out that the attenuation is 0.5 related to that distance. Now, the value of emitted intensity for the green for the diffuse part is 0.5. No, actually it should be 0.3. There's a mistake here. Well, that should be 0.3. I don't know why it's 0.5, but it should be 0.3. Okay, it doesn't matter, because the procedure is the same. I have to look into this. This is the first time I realized this. Then what you have to do, in order to get the intensity for diffuse for the green, you have to apply Lambert's law. You remember Lambert's law? It's the normal. It's the girl sunbathing on the beach. Okay, so it's her surface, so her orientation, and the position of of the vector between the point and the light source. Well, L basically. This has to be multiplied by the KD, which is the absorption coefficient, and by the intensity factor subdivided by the attenuation. So it turns out that the value of intensity is 0.243. This is an intensity value. It's not the green quantization step. If you consider that usually a monitor which is displaying completely black has an intensity of 0.01, something like that, you can understand this is a green, well, darker of course, but not very dark. So it's still light. This is the diffuse part. Then there is the specular contribution. I'm choosing conventionally a non-metal shininess. Any number below 100 would have been acceptable. Here, because I hate making calculations, especially to the power, I choose 1. Look how my, as a fox. Like the fox I am, I choose 1. So you also can be foxes. So choose 1 instead of, 4.5, and then calculate what it is to the power of 4.5. 1. This is LGS 0.2, which was correct, I hope. Yes, LGS 0.2. And here you apply the Phong in bed in the Sunday morning with sun formula, which is perfect reflection and position of the viewer, because it's important where Phong is in the bed and what does he look to the reflection from the window. So it's reflection, scalar, position of the viewer, right? So the shininess multiplied by the absorption multiplied by the intensity emitted for the light source for specular divided by the attenuation that I already calculated. And it turns out that this value for the specular part is 0.097. The total contribution is the sum of the two. It turns out that the intensity for the green is 0.34. Last part, I know that I have 256 levels because I have a 24-bit depth buffer. As a convention that I didn't mention in the text, but I mentioned in the theory, we say that a general monitor, when it is completely black, actually it's not true that it's completely black because it always emits some light, right? We conventionally express that light that a black monitor emits as a 0.01 intensity. So, given the base of my logarithmic scale in 256 steps, the level at which 0.34 finds itself in a logarithmic scale starting from 0.1 and having 256 steps, 0.34 is located between 196 and 197 as a step. Is in between. Here I choose, I say that is 196. Okay? So the green level, the green quantization step 196, more or less expresses the value of 0.34 of intensity. Right? So my color to put in my frame buffer will be red 0, green 196, blue 0. Okay? Is it engineering enough, concrete enough? That's what we like. Okay, you should be more or less able to conduct yourself. Where are the pitfalls here? Oh my God, it's not a point source, but it's what is the other type? I don't remember. Spotlight. There you are. That's one pitfall. Another one is you have the red channel and the green channel. The green channel. So you have two colors. So you don't have to sum them together. Okay? Because they are two colors separate. So if you copy from this example, you go wrong. Okay? So you see, the example will be similar, but there could be these variations. Okay? So in the end, you have to understand what you are doing. Otherwise, you fall into the pitfall. And I'm sorry. No points for you in that case. You don't have to fall in the pitfall. Okay. So that basically covers the part of illumination. We have a model. We have a theory to follow. We know more or less how to make our calculations. Then there is another part which is called shading. Shading is a technique that is applied to quickly distribute color over the polygon. The illumination allows me to decide the color in a specific point. But shading gives me a policy to color the whole object. To give you an example, the flat shading policy goes like this. Determine the color of one vertex of the polygon. All the other vertex and all the other points inside that polygon have that very same color. That's why it's called flat shading. Because if you use flat shading, you will see all the triangles of your mesh. Because every triangle is colored with the same color. So there is a neat difference, a very clear difference between two different colors of two different polygons. And in the end, if the polygons are not very small, but are big enough, you actually see all your mesh composed by different polygons. I think I have an example. Did you do with Raphael an example of flat shading? You didn't? Well, that's an example of flat shading. Didn't Raffaella have the time to show you smooth shading, flat shading? Well, to color meshes. You were sleeping during Raffaella's. Okay, I will tell her. And if she did, and I tell you that you don't remember, I think that she will come here. You know her. She's quite a determined type. Okay, but anyhow, this is flat shading. And I announced that you should know about this. So if you don't remember how to do that in OpenGL, go to the Red Book in the shading chapter and make the exercise on how to shade meshes. There are three basic types: flat shading, Gouraud shading, and funk shading. Flat shading is the simpler of the three. And the idea is that, well, you see there in OpenGL, okay, you just, it's just an instruction, GL shade mode, GL flat. It's not very complicated. If you do this, then you apply colors. Well, you apply an array of colors, and OpenGL automatically will shade for you the mesh which you're passing over in the array. You need the array of coordinates of vertices. Then you need the array of normals, and then you need the array of colors. If you pass these three arrays and you activate any of the three shade models, OpenGL will shade the mesh for you. If you activate the GL flat shade model, this is what you get. Every polygon has the same shade. This is fast, it's good for a preview, but it's not realistic and it's not accurate. So you may want something fancier to color, to shade your polygons. And, well, this is a slide which is supposed to tell you that, okay, this system is not very nice, and it also shows you a phenomenon which is called Mach bands. Mach bands is a perception, a phenomenon at the perceptual level, which has to do with the way our eye perceives color. The idea of Mach bands is, if you look, when there is a marked difference in tint between two colored areas, your eye tends to intermix the two tints at the border in this way. That you perceive in here, where the color is lighter, you perceive an even lighter intensity. And here, where the color is darker, you perceive an even darker intensity. So, for example, if you look at the Mach band over here, you see that there is a certain thing, but here you can see which is a little bit lighter, and here you can see which is a little bit darker than the other. Yes? And the same here, and the same here, and the same here. I didn't do anything to this image. It's just our eye, no really, it's just our eye that perceives it like that. If you don't believe me, I don't know, go and take, I don't know, your sister's art book, and take away some spaces of color paper and with a marked difference and put them together, look at it, and you will see that there will be Mach bands formed. Okay. So flat shading is a nice idea, but it's a little bit gross. So do we have something finer? We have Gouraud shading, which was proposed in a paper from Mr. Gouraud. That's why it's called Gouraud shading. The idea is that you have to take normals and it proposes to use a different normal well, let's say like this. When you have to decide a color, using the funk model, one of the four vectors is n, the normal. Gouraud proposes, until now, and with flat shading, you choose one normal for the polygon, and this normal is equal to all of them. Gouraud says that this is not true. Because, for example, at the intersection between these polygons, you're actually making an arbitrary choice. Because imagine that you are calculating n1. And you are using n1 to decide the color at this point. This may be correct, according to Fong model, when you are considering only this polygon. But if you're considering the adjacent polygons, then n1 is not the correct normal. So if we're computing again the color of that point, but using this polygon n3 with normal n3 as a reference, the color would be different. Why? Because the normal is different. You see? You see what I want to say? So the idea of Gouraud is to actually don't calculate a normal specific to a polygon, but calculate a normal as an average of all the surrounding normals. In this way, you get a normal which is more or less equal for all the surrounding polygons. Plus, in the scan lines which are between all the vertices, so in all the intermediate points inside the polygon, you linearly interpolate the color. Okay? So you calculate a color here with a normal which is the average of this. You calculate a color here with a normal which is the average of the surrounding. Now we have two colors which are different in the same polygon. The inside of the polygon is shaded with the colors interpolated in between those two colors. Okay? This is the idea. Fine? Then here we have Fong. Fong says, that's a nice idea, Gouraud, but there is an even smarter idea. Why limit ourselves in calculating interpolated normals at the corners? We will go on and we will interpolate normals at specific segments on the borders. So actually you're doing a double interpolation. So you're using this normal here in the Gouraud style, this normal here in the Gouraud style, and then you decide how many scan lines you want. It depends from your scanline resolution in between. For example, I want 3 in between scan lines. I'm using for that scan line not an interpolation of the color, but I recalculate the color with an interpolated normal. So it's, well, it's almost the same, but it's a little bit finer, more precise, okay? Because you are using the Fong model again with a recomputed normal. You are not interpolating the two colors. In Gouraud, you use the Fong model 2 times for getting 2 colors, or interpolate the colors in between. Here you use the Fong model as many times as the resolution of skyline you want in between. This is supposed to give you a more precise result. Well, it does. These are normal interpolation equations. It's a pity that I don't have an example here, but you can try for yourself. With OpenGL, now you know how to do it, right? With OpenGL, draw a mesh, assign the colors to the vertices, and then using GL shade mode, try flat shading, try Gouraud shading, and try foil shading. In the right book, there's an example assisted guiding you in doing that. GL smooth. You're right. Because you have flat and smooth. You're right. You're right. You have no Fong shading in OpenGL. You have Gouraud shading, which is this one, GL smooth. If you would want to do Fong shading, you would have to apply it by yourself. I think so. Thank you. Okay, so this is it. Do you have question about lighting? No questions? Okay, so we still have half an hour. I will use it to introduce the next topic, which is also a very interesting topic. But it is so difficult that exceptionally for this topic, I have a video of the lecture. So if you didn't understand the lecture, if you don't understand the lecture, you can follow the video. I have to say, though, that it is an old video and it is in Italian. Sorry. But, okay, you take what the convent gives. How we say in Italy? Land full of convents. You can translate for that, yes. Okay, what is the topic? The topic is curves and surfaces. Curves and surfaces. Curves and surfaces. The beauty of this topic is that it makes a simple and extraordinarily complex problem. Well, in this regard, it is similar to the illumination problem. The problem is how to draw curves with a computer. We give it for granted. But if you think about it, it's something which is extremely complicated. I mean, the thing that you can just fire up your Illustrator or, I don't know, Windows Paint, if you don't have the money for Illustrator. But, well, no, actually, I don't know if Paint is a suitable example. No, not really. Illustrator is a good example, Corel Draw. And you can draw a vectorial curve. You know how to do that? I mean, you fix a few points, and then there is a curve which is plotted along those points, and you just move the points, and the curve follows around. It's a vector. It's not, well, it's of course rendered in pixels in real time, but the computer, the program, thinks it as a vector. So it has the mathematics to represent that curve just by using points which are called control points. And that, if you come to think about it, is astonishing. Because what are the means that we know as engineering students for describing mathematically a curve? What is the way you would do it? With a function, with a polynomial. Okay? Y equals to 2x to the square plus x plus 1. That gives you a curve. Okay. But does it give you the curve you want? Yes? yes? Okay, you're thinking about the composition of function. Yes, this is something that I also will explain. It has to do with the geometrical continuity of a curve when you're constructing a complex curve out of a sum of smaller curves. And it's not that easy because you would like that your user moves a part of the curve and all the rest of the curve will follow suit. And if you really represent the curves as the touched part, that gets hard. So really, the first idea is I try to find a polynomial which fits the curve I want to represent. And this, of course, is next to impossible. Okay? I mean, I challenge you to try. I mean, I draw a curve, and then I tell you, what is the equation of this curve? Nice question. But this is exactly what we users do every day when we're drawing a curve with control points, and when we move one control point to, because we want the curve to take a different shape. And it's like we're asking to the software, what is the equation for this different curve? And the software cannot answer to us, I don't know, because it has to draw it. And in order to draw it, it has to know how to draw it. The solution came from cars. The problem was solved by Pierre Bézier, which was an engineer working at Renault Automobile. So Renault, apart from winning world championships in Formula 1, also giving us, nice cars, all in all, gave us also a breakthrough solution to the problem. That is, an engineer from Renault invented Bézier curves. They are called Bézier curves because he was called Pierre Bézier. And why did he invent that? Because he wanted, Renault is famous for cars with nice curves. Do you remember the Renault 4, for example? It was nice, strange curves. And they wanted to start drawing, not with the usual drawing board, but using the computer, with CAD. And at that time, that was a problem, because CAD technology, computer-aided design, at that time was not extremely sophisticated, and one of the big problems was that it was not possible to draw, in a simple way, curves, which seems astonishing now. So we solved the problem, implemented the algorithm and the mathematics beneath that to draw curves with the CAD. And now we will see how it was done. So we will see, the story starts from parametric curves, which in one step further from handling the curve as a polynomial. There is a little bit, a small refinement, which is using it as a set of parameters, which is not much better, but still better than using the polynomial. Then we will see Bézier curves. This is the real breakthrough, the real invention. B-splines and nerves are refinements, but the real invention is Bézier. The idea here is using an equation which averages the position of the curve using a set of coefficients which have an averaging power. They are magical coefficients. I will show them to you. They are called Bernstein polynomials. That's what the Bézier curves do. B-spline uses the same approach, but the set of coefficients to calculate the position of the curve is not the Bernstein polynomials, but is a function which is called the Cox-de-Boer recursive function. I will show it to you also. And NURBS is an extension of the B-spline, which can also be applied to rational and non-uniform curves. We will see that. Everything that we will say to curve can be extended one step, or you can better say one dimension, and go from curves to surfaces. As soon as you know how to draw or to represent a curve in a nice fashion, you can start representing two curves and make a surface out of them. That's the idea of going to surfaces from curves. And after we have seen that, we will see how you can use your knowledge, because you will have new knowledge, I hope, of representing curves in OpenGL. So you also can draw very quickly and very clearly curves and surfacing using OpenGL. What are the tools that OpenGL gives you to draw curves and surfaces? The fact that we have to face all the theory that we are going to face is because the OpenGL commands to draw curves and surfaces really requires you that knowledge. It starts asking you, what is the stride of the curve? Is the curve clamped or not clamped? Etc., etc., etc. And the answer has not to be, what do I know? I don't know anything about this, because you have to know the theory of Bezier curves in order to use the evaluators in OpenGL. Okay, well, our first idea in tackling the problem of curves was to use curves in their parametric representation instead of their equation, polynomial representation. This is hardly an improvement because you know that is actually, sometimes it's just a rearrangement. Sometimes there is a real different representation. But basically, in the idea of parametric curve is that you have a set of equations based on a parameter that gives you the line. This is a 3D line with a base point and the direction vector, with this, which is this one, d1, d2, d3, and u, which is the parameter. It's hardly different from the vector representation of array. Okay, it's practically the definition of array. Do you remember the definition of array? Okay. These are very verbose, but don't you worry. In general, you can, as in the straight line, you can define a parametric curve in space with a parameter which goes from 0 to 1 closed. And to do that, of course, you have to give an explanation of how the x-coordinate behaves with the parameter u, how the y-coordinate behaves with the parameter u, and how the z-coordinate behaves with the parameter u. We are bidimensionally. I mean, it's a curve in 3 dimensions, so you just need one parameter. Using this tool, I could already start thinking, okay, I can make complex curves by using simple parametric curves and joining them together. But the problem is, so this is what our colleague over here said 5 minutes ago. When building curves and surfaces, boundary curve segments are meeting between each patch and meeting and interjoining vertices. So we can imagine to have two curves, f over the parameter of u and g over a different parameter v, when u and v are values in intervals a, b, and mn, respectively. We have one problem. We have to make sure that these curves join together in a smooth way, so that there is no geometrical discontinuity, so that they look and behave like a single curve. We have to ensure smoothness. To ensure smoothness at the joint point, we need to introduce two concepts: the concept of continuity and of class of continuity. So in general, when we draw complex curves by creating compound curves, that is, curves made by joining together simpler curves, in order to make a shape that works, that looks feasible, we need to join these curves in a nice way, in a smooth way. How we can be sure mathematically that this is true? By applying the definition of parametric continuity. So we have to check if the parameter is continuous on the joint point between the two set of parameters, the two set of curves. So the situation is, well, I think you can visualize it, but just to make a drawing. In order to trick my viewer, we need to check if there is geometrical continuity at the joint point over here. Here we have, if U belongs to 0, 1, V belongs to 0, 1, here we have F0, here we have F1, here we have G0, here we have G1. Okay? If I draw it like this, you can already start thinking by yourselves at some rules you have to check to ensure mathematically continuity. Look, maybe the problem puzzles you because you say, but I see that they are continuous. It looks good to me. Okay, but you have your eyes and your brain. Remember that we are studying ways to check this mathematically to explain to a computer. So we have to check with the software if this joint, this compound curve is legal, is good or not. Okay? So what are the mathematical rules that we have to check at the joint point to verify that we have suitable continuity? Well, now I've put here some hints. Okay? What is the very, very, very first rule that you would check? To check that they join. That F1 equals to G0. Okay? Very good. That's the continuity criterion of class 0. Does it suffice? Why doesn't? Right. Because maybe this is a nice situation. But as many times in life, not always you have a date with Monica Bellucci. Sometimes you have a date with Rosy Bindi. So, this is the date with Monica Bellucci, and this is the date with Rosy Bindi. Here, it seems nice. So, your continuity criterion is satisfied. You see? But does it look good to you? No, there's a surprise here. Okay, so we need another criterion of continuity. Okay, let's not delve further in which kind of surprise. But the surprise here is that we have something that we wouldn't expect. Okay, it's 5 o'clock in Friday evening. Don't be hard on me. Well, come on, you have understood. What is the second criterion that you have to check? The derivatives, the first derivative. You need the first derivative and the second derivative to check. That's called first class continuity and second class continuity. Of course, you can be more strict than that and ask for n continuity. That is, the derivatives until the n derivative coincide. It really depends from what you want to do and how much deformation you think you will perform on a transformation you think you will perform on the compound curve. Okay? Oi, oi, oi. I'm not a serious one. I'm just doing this for fun. Okay, so, we have considered the right end of the curve FB and the left end of the curve GM. If FB and GM are equal, as shown in the above figure, which I have drawn, we shall say that the curves F and G are C0 continuous at FB equals to GM. If for all I less than k, the IF derivatives at FB and GM are equal, we shall say that the curves are CK continuous at that point. This is what we have discovered together. Intuitively, two curves are C0 continuous at the joining point if we can go from one curve to the other without crossing a gap, because these two curves connect to each other. The first class continuity is the simplest and most used continuity. Usually, it's used for visual purposes, so you want to assure visual continuity. If you want However, if you want the user to perform a transformation or scaling on that curve, the first class continuity is not enough anymore. You can understand that. Imagine scaling the curves. If you have just first class continuity, then you form a Rosy-Bindi problem. Okay? But if you have second or third class continuity, not. The scaling goes through in a more nice way. So, but usually, if you stick to first class continuity, the first derivative of f in 1 and the first derivative of g in 0, they are equal, you have continuity of class C1. In this case, the two curves will have at the joint point the same tangent vector, as we would expect. In general, the higher the degree k of continuity, the better the result in modeling a compound curve. A curve shaped composed by joining several curves. Okay. You know what? I think that we might call it a day. And I would like you, if you can, please, next week we meet again, and we go on with the curves and surfaces. But since you didn't start study yet, you should start study. Review all the geometry that we did in lesson number 2. Review bounding volumes. Review visibility determination, and review illumination and lighting. I need you to be fresh on that the next time. Okay? Please, because otherwise you arrive at the end and you realize you didn't understand anything. So the next time we will start with some question and answer session, meaning that you make the question and I will make the answer. So it turns okay for you for this time. But it's in preparation for next time when I will be making the questions and now you will be saying the answers. But I want a few questions. Thank you for your attention and have a nice weekend.